Okay, your labs are due this morning. So if you have not finished your lab, please make sure you get it done by like, I don't know, the end of class or something like that. So I feel like I've given plenty of time. So please make sure you hand in those labs. But we're going to move on to Ka and Kb expressions. We're going to do our quiz in the last half of class, or in the last like 25 minutes of class, like we always do. So kind of veg out until then. The ability of an acid to ionize in water, known as the strength of an acid, is often reported as the acid ionization constant Ka. When I say Ka, you need to do a little bit of almost like word association. What is capital K? What is that always kind of related to? Equilibrium constant, right? And so it's an equilibrium constant for what? An acid reacting with water specifically. Ka is always acid plus water. It gives hydronium and conjugate base. That's always what it is, okay? Acid plus water gives hydronium and conjugate base. And we can tell if this is a strong acid or weak acid by looking at the K. We define a strong acid as being greater than 1, right? So basically what that means, strong acids almost completely ionize, right? 99.99999%, okay? So they're going to make way more hydronium, and there's going to be very little of the original acid left over. Weak acids, a tiny amount turns into hydronium, and very, very, very large amounts of the acid will be left over. We were practicing writing the Ka expression for some different things. So what's the Ka expression for propanoic acid? Well, it's propanoic acid plus water gives hydronium and propanoate. So you just put hydronium and propanoate on top and propanoic acid on the bottom. Why are we ignoring water? It's a liquid in a heterogeneous reaction. A liquid in a heterogeneous reaction. Perfect. So let's take a look at oxalic acid. And let's write the Ka for oxalic acid. First thing I want to bring your attention to is you cannot write an equilibrium constant unless you have a chemical reaction. You need a chemical reaction. So what's going to be our chemical reaction here? Does anybody know what oxalic acid is? Oxalic acid plus water. Wow, it's an acid plus water. It's okay. Acids always make hydronium. And we're going to be left with the conjugate acid or conjugate base of oxalic acid. Go ahead and write down what the conjugate base of that thing is. And then go ahead and write down the Ka. You finished this for me. I did most of the work. I want you to tell me, is the Ka for this reaction greater than 1 or less than 1? You can look it up in your data book. Is the equilibrium constant for this particular reaction, is it greater than 1 or is it less than 1? It's less than 1, right? It's not like significantly less than 1, but it's still less than 1. So when I look at the Ka for this reaction, when oxalic acid turns into hydrogen oxalate, it has an equilibrium constant of 5.6 times 10 to the negative 2. 5.6 times 10 to the negative 2, that's not the tiniest constant we've ever seen. That's 0.056. That's not tiny, but it's still less than 1. So let's think about this. If the Ka for this reaction, is 5.6 times 10 to the negative 2. I'm curious, what are we going to have more of? Once equilibrium is established, what are we going to have more of? Are we going to have more hydronium, or are we going to have more oxalic acid? Why? Yeah, this means reactants favored, right? Favored, that's terrible, whatever, okay. So what that means is that there's a high concentration of this, and there's a low concentration of everything here, right? That's what's giving us a tiny, like relatively tiny equilibrium constant. So if I were to ask you, which one of these is greater concentration at equilibrium? Is hydronium greater or is oxalic acid greater? You'd be able to tell only from the Ka. That's all you need. That's all you need in order to figure this out. Is that kind of okay? Okay, good. Perfect. So let's take a look at a solution of 2 different acids with the exact same concentration. So let's make a 0.10 mole per liter solution of hydrochloric acid and a 0.10 mole per liter solution of HF. First thing I want you to think about. HCl, is it strong or weak? Strong. It's strong, right? So that means because this is strong, this is basically a 100% reaction. So I'm going to show you something. I can do this because I can move things around on the smartboard. You can't, so deal with it. Okay. So we're going to have some HCl. So here's my beaker of water, and as soon as I put a molecule of HCl into my beaker of water, here's my beaker of water. The moment I put that HCl in there, what is it going to turn into? It's every single time it's going to turn into H3O plus and Cl minus, and then those 2 ions are going to float away from each other, right? Okay, perfect, no problem. I'm going to put another HCl in here. Immediately, once I put that other HCl in here, what's going to happen? It's going to break up. It's going to ionize in the water, right? So I'm going to put another one in here, H3O and a Cl minus. And I'm going to put another one in here, and what's going to happen? Okay, same thing. Goodness gracious. H3O and Cl minus. Hopefully, this is just reinforcing kind of what I told you a few days ago, where does HCl exist in water? No, when you buy a bottle of hydrochloric acid, do you get any hydrochloric acid? No, they're lying to you. You should sue them for false advertising. But whatever, that's fine. We can deal with it. Now let's take some HF. HF, is that strong or weak? That's weak, and you can tell from the Ka listed on in your data booklet. So what that means, this means typically less than 10%. We'll say less than 50%, but typically it means less than 10%. So I'm going to take some HF, and I'm going to infinite clone. There we go. So I'm going to put some HF into my water. And what happens to the first one? Yeah, maybe it breaks up. So it ionizes to be H3O and F minus. Then I'm going to add another HF. What happens? Yeah, it doesn't. It doesn't break up, right? Because typically less than 10% of our acids will ionize if it's weak. So I'm going to add some HF, and there you go. These two solutions have the exact same concentration of hydrogen chloride and HF. How many HCl's did I add to this beaker? I added 3. How many HFs did I add to this beaker?
3.
I added 3. They have the same concentration. I added the same amount to both beakers. So now let's take a look. What are some properties of these two solutions? Which one has more hydronium? The strong acid. Would you agree? This one has more hydronium. So consequently, if this has more hydronium, will it have a higher or lower pH? It'll have a lower pH. Does that make sense? This will have a lower pH than that, even though they're the exact same concentration. Because one's weak and one's strong, they'll have a different concentration of hydronium. So this one right here will have a lower pH, and this one here will have a higher pH. I don't mean higher as in higher than 7. I just mean they're both acidic, just one's lower and one's higher than each other. Okay. This is a blast from the past. See if you guys can get this. Will this solution conduct electricity?
Yes.
Why? Does it have charged particles inside the solution? Anything with charged particles can conduct electricity. Okay? So anything with any solution that contains ions will conduct electricity. Can this one conduct electricity? Yeah. But not as good. Is that okay? One of these will conduct electricity better than the other. They're still both conductive, but one will turn on a light bulb more brightly than the other. Okay, all right, no problem. So this one is going to be very conductive. And this one is going to be a little conductive. They're still both conductive, right? Acids make hydronium, and hydronium is an ion. So any acidic solution will always be conductive. It just depends on how much hydronium there is in there. That's all. Good. I didn't know if people were going to be able to get that. That's fantastic. Can we move on? All right. Fantastic. Okay. Damn it. Hey, is yours underlined here? Is acid number 1 underlined?
Yes.
Ah, man. I've changed that probably 5 times, and I save it every single time, and it always comes back. I don't know why. Okay, whatever. Doesn't matter. So, order the following acids from strongest to weakest. Could you do this? Could you do this?
Yes.
Okay, do it. Order them from strongest to weakest. You're just going to go 1, 2, 3, 4, or 3, 2, 1, or whatever. Remember, the larger the Ka is, the more hydronium it will make. This is more of a numeracy problem than it is anything else. I'm seeing some people make the same mistake that I expect them to make. Okay, which one of these has the largest Ka? Don't say anything. Don't say anything. Hands up if you think acid number 1 has the largest Ka. Hands up if you think acid number 2 has the largest Ka. Hands up if you think acid number 3 has the largest Ka. Hands up if you think acid number 4 has the largest Ka. Interesting. Okay. Well, let's try and think about this. It's definitely got to be acid number 1 or acid number 3 because they have the lowest negative power. Does that make sense? 3.6 times 10 to the negative 5, that's 0.0000, okay? Whereas this has 6 zeros, or 5 zeros, or whatever, however we want to call it, and this has 9 zeros, or 8 zeros, right? So definitely it's going to be 1 or 3. Now, the class was split. I don't know if you saw that. It was kind of split between forward and back, so which was kind of unfortunate because some people at the front thought acid number whatever, and then some people at the back thought acid number whatever. I'm going to write this in a different way. 0.000036. Would you agree this is 3.6 times 10 to the negative 5? Perfect, okay? 9.4 times 10 to the negative 6. 0.1234594. Good, perfect. And I'm trying to line up the zeros and the other digits, okay? This is 0.000047. And then this is 0.234567812. Would you agree the smallest, weakest, like the smallest K, the weakest acid is going to be number 4? Okay, sure. So that one's out. Then the next weakest acid is going to be acid number 2. Okay, so that one's out. Then let's take a look at this. I'm going to take that. All right, whatever. Okay. Which one of these is bigger? Is acid number 1 bigger or is acid number 3 bigger?
Number 3.
Acid number 3. Does that make sense? You're looking for the smallest negative exponent, like power, but you're also looking for the largest number, okay? Look for the smallest negative exponent first, then the largest number if there's a tie. So this should be 3, 1, 2, 4. That's just, that's going to come up eventually, okay? It's going to show up and whatever. That's totally fine. Okay, I'm going to give you, we're going to kind of read through this and I'm going to give you 20 seconds to kind of analyze it. It's going to be quick, but that's fine. In this benzoic acid solution, it doesn't even matter. You don't even have to read the words. Don't worry, the English words are probably going to screw you up more than anything else, okay? In this benzoic acid solution, this is benzoic acid. It's reacting with water to make benzoate and hydronium. Is benzoic acid a strong or a weak acid? It's a weak acid. So now try and figure out which statement qualifies the best. Benzoic acid concentration is equal to the benzoate. Benzoic acid is greater than. Hydronium is equal to. Hydronium is greater than. Blah, 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 blah. Give you 20 seconds to read them and pick the correct answer. Matthew. Okay, let's think about this. What's going to be greater? Is the product's concentration going to be greater or is the reactant's concentration going to be greater? Yeah, this is reactants favored, so the reactants are going to be greater. So these things here are going to be higher than those, right? So let's see which statement best describes that. Is the benzoic acid concentration equal to the benzoate ion concentration? Are the products and reactants equal to each other? No. Benzoic acid concentration is greater than the benzoate. Would you agree? Benzoic acid is great. Oh, boom. Okay, done. Don't even have to look at the other ones, right? You don't even have to worry about it. These questions are tough because they're trying to screw you up with the English language. And the English language, I think we can all agree, sucks at least a little bit sometimes. I don't like it, but that's fine. That's coming from a guy who is always terrible and never put any effort into it at all. So if a question gives you the pH of a solution, you should be able to determine the equilibrium concentration of hydronium after the acid has ionized, okay? Now let's think about this for a second. I've got a beaker of water, and I add some acid. I'm just going to say HA for whatever, random acid, doesn't really matter. I add some acid into here. Before I added the acid, as long as this was just pure water, was there a ton of hydronium in there before I added the acid? No. Okay? If this is pure water, there's not a ton of hydronium. There's a little, because water can ionize itself, but there's not a ton. So the majority of the hydronium in an acidic solution comes from whatever acid you put in it. Hopefully that's not confusing, right? So when I put this HA into the water, it turns into H3O. That means that H3O that we measure from the pH is always an equilibrium concentration. Okay? Whenever you're measuring pH, you're really measuring hydronium concentration. pH is hydronium concentration. Would you agree? Without hydronium, there would be no pH, right? So pH is an indirect measurement of the hydronium concentration. The concentration of the acid is always the initial in the isotable. If I add 0.1 mole per liter of an acid, then that's the initial acid concentration. Okay, we're going to do some questions. Now this is like a fundamental big block, okay? This is hugely importante. This is kind of the beginning of the actual meat and potatoes of this booklet. So, what is the Ka for vinegar if the pH of a 0.1 mole per liter or a 1 mole per liter solution has a pH of 2.37? You could look up the Ka for vinegar. Vinegar is just acetic acid, right? Go ahead and look up in your data booklet the Ka for acetic acid. Go ahead. Look it up. You have a data booklet. What is the Ka for acetic acid? Is it 1.8 times 10 to the negative 5? Okay, perfect. So we already know that that's the Ka. Well, how do people measure the Ka of a solution? How do people know that? Is that did we just get handed that information by some omnipotent being? No, we figured that out. And here's how we figured it out. We made a 1 mole per liter solution of acetic acid. That should be pretty easy for you to do in a lab, okay? You take acetic acid, you add enough into water to make 1 mole per liter. That's a standard thing that you did in Chem 20 a few times, okay? So that should be fine. Then you take that and you take a pH probe, right? You stick the pH probe in it and you measure a pH of 2.37. This is all stuff we can do in the lab. So now let's see if we can figure out how to measure the Ka of something. Initially, how much acetic acid did I put in that water? 1 mole per liter. Is that okay? I put 1 mole per liter. Does the concentration of water change throughout this experiment? No, because it's a liquid in a heterogeneous reaction, so we don't care about it. Acetate. Now this is I want to be very clear. Before you added any acetic acid, was there any acetate in the pure water that you started with? No, there was none of this. And before you added any acetic acid, was there any hydronium in the pure water that you started with?
I mean, the ionized itself.
Technically there was 1 times 10 to the negative 7, but we don't care about that, okay? That's so small that we don't care about it. Now, we can't really complete the rest of the table unless we know a little bit about an equilibrium value here. Now, where's the only place how do we make hydronium in this reaction? Where does it come from? The acetic acid. So once we added the acetic acid, then we measured the pH. Remember, that pH is a measure of the equilibrium hydronium concentration. So let's calculate the hydronium concentration from the pH. Does anybody not remember the formula for calculating hydronium? Or does anybody remember the formula for hydronium?
Yes.
It's what?
10 to the negative.
10 to the negative pH. Good. You should get 0.004265, blah, 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 blah. Are we done the question?
No.
Then we can't round. All right, moving on. Moles per liter. Okay, so that's our hydronium concentration at equilibrium. 0.004265. Now I'm curious, can we complete any one of these 3 columns? Yeah. If you started with 0 and you ended up with this, do you know what your change is? Yeah. Did you add or did you take away? Yeah, you added this much. So immediately you should recognize that if we're adding here, adding x here, we should add x here, and we should take away x here. Why am I adding x's on this side and taking away 1x on that side?
Because it's one side added if that's shifting up the other side.
Good. Yeah, that's perfect. If I'm making hydronium, what else am I making? This thing. Acetate, right? Name doesn't really matter, but whatever, we're making that. So, if we made this much hydronium, then how much acetate did we make? The exact same amount. Do we remember this from a couple weeks ago? Yeah, okay, all right. Plus 0.004265, blah, 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 blah. So what should be my concentration of acetate at equilibrium? The same thing. Blah, 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 blah. Okay, now do we know how much we're losing here? Same number. 0.04265. And so, okay, that's fine. We're going to be left with a 0.995734, blah, 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 blah. Could you calculate the K value for this reaction?
Yes.
Yeah. The K value for this reaction is this relationship, right? All of the equilibrium concentrations in that expression. So Ka is equal to acetate concentration times hydronium concentration divided by our original acetic acid concentration. Please tell me you get 1.827 or something like that. 827 blah 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 times 10 to the negative 5. Are we okay with that? Yeah? Okay. Okay. Now let's take a look. How many significant digits should we have in our final answer? 2 or 3? 2? 3? 2? 3? 2? 2? 3? 3? 2? Okay. Let's try it out. Go back to our original information. How many significant digits here? 3. How many significant digits here? 2.
Oh, the yes, how was
Right? It's only after the decimal place for pHs. If I give you pH of this, you don't care about that first, anything in front of the decimal place doesn't matter. That's just telling you that there's approximately 2 zeros before you actually get to your significant digits.
Oh.
That's all it's saying. Approximately 2 significant digits before you get to your actual significant digits. Does that make sense? Okay? So these are your only 2. So we got 2 significant digits, so we could have rounded, not really, right? Because we're not done, but anyways. Could have rounded to 2 there, could have rounded to 2 there, should round to 2 there. So what's our actual answer? 1.8 times 10 to the negative 5. Okay. So when you look at your data booklet, all of these KAs, how many significant digits do they have in all the KAs? Dose, right? And the reason why is because when you measure pH with a pH probe, it's really incredibly difficult to get an accurate pH reading. It's infinitely difficult to get a really super accurate pH reading. So what I'm trying to tell you is that there's actually a lot of uncertainty in this measurement. Because there's a lot of uncertainty in this measurement, there becomes a lot of uncertainty in that number. I'm telling you right now, this is not a very accurate representation of the actual Ka of this acid. It's the best we can do, okay? And this is going to show up a little bit later. This being an inaccurate representation is going to have consequences here in maybe 10 minutes, that kind of thing. Okay, so if we wanted to figure out an unknown acid has a pH of 1.17 at 0.4 mole per liter, what is the Ka of the acid? Could you do this? Could you solve this? It's the exact same thing as before, right? An unknown acid has, what's its concentration? 0.4 mole per liter. And what's the pH? 1.17. This is the exact same thing that we just did, except it's an unknown acid. How do you want to represent, what chemical formula do you want to represent an unknown acid? HA. Does that make sense? Just choose HA. Other options, you could choose HX, right? X being unknown. Is going to react with water, right? Anytime you have Ka, Ka means acid plus water. What are we going to make here? We're going to make hydronium
Make
and A
minus.
minus. Good. If we lose a positive here, we're left with the negatives left over. We should be able to fill this out. We should be able to go through this and kind of, do this a little bit. Do you know what the initial acid concentration was?
Yes.
Yeah, 0.4. Nobody cares about water because it's a liquid in a heterogeneous reaction. Do you know how much hydronium we initially had? Yeah, you do. No, you do. Absolutely, you do. How much acid? How much hydronium was in there before we added the acid? Zero. Oh, that seems pretty straightforward. How much conjugate base was there before we added the acid? Zero. Oh, okay. Then all you have to think about is what the hell does a pH of 1.17 actually mean? Remember, that's an indirect measurement of the hydronium ion concentration. Six, 7, 6, 0, 8. When I say pH of 1.17, how many zeros are in the hydronium concentration? How many zeros before you get to the actual significant digits? 1. 1 0 before you get to the actual significant digits, right? That's kind of what it's telling you. Could you complete this? Could you physically complete this? Okay, I'm not going to complete the rest of it. I'm going to leave this as a little bit of like work for you to do on your own. Trust that I have put the correct answer in the bottom corner of this slide. So you should get 1.4 times 10 to the negative 2. I'm going to give you like a minute. I'm going to walk around. You can ask me any questions you want. You do what you got to do. Totally, keep going. Can we complete any poems? We don't have any more religion. Okay, so continue the song. But you're not going to be able to do religion. Well, what are we going to have here? Here. There will be an approximation. I don't know if you remember that approximation. I don't know if you stuck around long enough. That's quite all right. Okay, I'm going to stop people. Hopefully, did you actually get an answer of 1.4 times 10 to the negative 2? Okay, good. Now, what is the unknown acid? What is the identity of the unknown acid? Do you see how that works? One person sarcastically and pedantically said, "Wow, thanks." Yeah, take a the more you say it, the more power it gives me, okay? I'm like a Sith Lord in Star Wars. So 1.4, the more you hate me, the more power I get. 1.4 times 10 to the negative 2, that is sulfurous acid, right? Okay? So I could totally ask you that on an assignment or a test or something like that. Now, please keep in mind, like, if you got an answer that said 1.5 times 10 to the negative 2, is 1.5 times 10 to the negative 2 close enough to this? Remember, there's error in pH measurement, right? So that I just want you to be very aware. Just take, if I ever ask you, just take the value that's the closest. Okay, all right, whatever. Okay, perfect. Now, what is the K for an unknown acid if it's initial and has a pH? No, we're not going to do that. This is the same thing over and over and over again. We got 10 minutes-ish to be able to debut this. Now, this is the part that really screws people up. We're going to do something a lot like the square root problem that we did in the previous chapter, the first half of this unit. So just pay attention. Just try and keep with me for right now, okay? Now, I'm going to give you a weak acid, and I want you to predict the pH, okay? So let's walk through a problem. Predict the pH and hydronium ion concentration of a 0.30 mole per liter solution of methanoic acid. What the hell is methanoic acid? What's methanoic acid? What does meth mean? One carbon. It means an acid with one carbon attached to it. So look in your list for methanoic acid. Look for methanoic acid. Yeah. It's got another name. Formic acid. When I add methanoic acid to water, what's the only other thing it can react with? H2O. What do acids always make in water? Hydronium and whatever the conjugate acid is, HCOO minus. Okay, predict the pH. What that means is, are we being given the pH straight off the bat? No, so we can't get this value. So that means we're not going to be able to complete any one of these columns. So we'll fill it in, but whatever, that's fine. 0.3. Water nobody cares about because it's a liquid and heterogeneous reaction. How much hydronium did we have in our pure water before adding the formic acid? 0. How much formate or methanoate did we have before adding the formic acid? 0. Okay. Can I complete any of these columns? No. All right, whatever. So let's try this. Let's use some other tools in our tool bag. Am I going to increase or decrease my concentration of formic acid? You're going to decrease by how much? 1x, right? Am I going to increase or decrease my hydronium? So increase, because if the reactants go down, the products have to go up, right? So plus x plus x. Well, that's the only way I can solve this. By using those x's. That's the only way that we're going to be able to do this. 0.3 minus x, x, and x. What's the only other piece of information you know about formic acid or methanoic acid? What's the only other piece of information? You know the Ka is equal to what? Jaden?
1.8 times 10 to the negative 4.
1.8 times 10 to the negative 4. I'm assuming that's correct. Can you use these values, even with the x's in here, can you use these values and make that equal to the Ka? Yeah, you can. You absolutely can. So the Ka is equal to our products, right? So H3O plus, what's H3O plus raised to the power of? H3O plus raised to the power of, what's in front of it? 1. Oh, okay, all right. And then methanoate raised to the power 1 divided by our methanoic acid. Okay, let's go ahead and do this. Let's go ahead and write it down. The Ka was actually 1.8 times 10 to the negative 4. What are both of these things on top? What are they both at equilibrium?
From where did you get the Ka?
I got it from the data booklet. When I look at methanoic acid, you just go off to the side. It's got a Ka of 1.8 times 10 to the negative 4. So you have that. You have the equilibrium value for this particular reaction. I want to get this done before we come. So what's my concentration of hydronium at equilibrium?
X.
Ah, man. Okay, X. What's my concentration of methanoate at equilibrium?
X.
Oh, okay, what's X times X?
X.
X squared, no problem. What's my concentration of formic acid at equilibrium? 0.3 minus X. Now, I want to be very clear. With these acids, anytime these acids ionize in water, they produce a tiny, tiny, tiny insignificant amount of hydronium. Not insignificant, we can still measure it, right? But this is like saying, Mr. Walton has $3 million, and then he goes and buys a coffee for $5. Does he still have $3 million?
Yes.
Okay, strictly speaking, no. But also yes. Because when I say I have $3 million, I don't, okay, but whatever. When I say I have $3 million, am I giving you all the information? Do I have exactly $3 million in my bank account? No, I have approximately $3 million. So when I have approximately $3 million and I lose approximately $5, approximately how much is left? $3 million. Okay? And this is the reason why. What is this equal to? What is this expression? X squared divided by 0.3 minus X. What is it equal to? Ka. And is the Ka extremely accurate? No. So we're going to make an approximation. We will always be able to make this approximation. You know what? Yeah, that's 0.3 minus X. Yeah, we're losing X. But, yeah, let's just ignore it. That minus X, ignore it. Because it doesn't really matter. When you lose a tiny little bit off of a huge number, it doesn't really change that much. Okay? So that's the approximation that we're going to do. So, if I rearrange this for X, if I want to get X by itself, all I have to do is multiply the 0.3 up. X squared is Ka, sorry, not Ka, 1.8 times 10 to the negative 4 times 0.3, right? So what's the only last thing I got to do to get X by itself? Square root it, right? Square root. So take the square root of that whole number. Did you get 0.007348 blah, 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 blah? Okay, that's X. But what is X really equal to? The hydronium concentration. That's what it's really equal to. We found our hydronium concentration. Could you, as our last step, now find the pH if you know the hydronium concentration? Yeah, you could. pH is negative log of the hydronium. So we'll take the negative log of that number. And you should get 2.13. Is that okay? Is that what you got? I'm looking for reassurance. I'm like a tiny child. I need to be reassured at all points in time. Okay, so that's it. That's all we're going to cover today. Okay, we went through a lot. So we went through a lot of information. Okay. So I'm going to give you your quiz now. Now I personally don't think this quiz is going to take very long. But as always, you've got tons of time to do it.